briefly spread what we're up to here with regard to energetic materials as manufacturing. And thank you everyone for tuning in. My name is Jorge Castellanos, and I am a chemist at Naval Surface Warfare Center, Indian Head Explosives Ordnance Disposal Technology Division. Alongside me is my colleague, Mr. David Zamora.
Hello.
He's a chemical engineer, and he has also worked on energetic materials additive manufacturing projects under the Navy. So just to give you a feel for what we do here at NSWC, we are a field activity of the Naval Sea Systems Command, and it's the Navy's premier facility for ordnance, energetics, and EOD solutions. We are the Navy's manufacturing technology center for energetics. We are the largest Department of Defense full-spectrum energetics facility. We cover the life cycle of energetics from research and development, engineering and testing, manufacturing, retrofitting, and disposal of energetics, allowing energetics to be sustained as a national asset. We are the nation's only design and development facility for underwater warheads and explosives. So our focus is on energetics RDT&E and in-service support and disposal for ordnance, and to provide the warfighter solutions for detection, location, access, identification, render safe, recovery, exploit, and disposal of explosive ordnances globally. And we provide real-time technical support to explosive ordnance disposal responders. So with regard to energetics, the breadth of which covers explosives, propellants, pyrotechnics, reactive materials, related chemicals, and fuels. Energetics are used in propulsion systems as well, as will be found in ejection seats for our Air Force and Navy jets. Our cartridge actuated device, propellant actuated device Joint Program Office provides life cycle management for the joint services. These would be our ejection seats. So with JPO, for the Joint Program Office, CADPAD, and our sponsor, Navy Mantech, there's an ongoing effort to be able to print solid propellant grains that are used in cartridge actuated devices that go into these jets for the Navy and Air Force fleets. The grains are used in cartridges to help eject pilot seats out of a plane, essentially. So we're looking to provide an alternative production method that complements CADPAD needs. Most of our work that we're going to discuss now was performed in 2018, and we had found very promising results where we've been able to repeatedly manufacture these grains. As far as how much we've been able to produce, these are meant for small batch quantities that would really fill in a gap where there is a need.
Hi, this is David Zamora over here. So I'll be talking a little bit more about the hardware that we use to do our work on. Here at NSWC Indian Head, we have various machines at our disposal, but for today we're going to be focusing on our main workhorse machine, which is the Fisnar F9000N, which it has a rather large build volume for as compared to a conventional 3D printer. It measures about 600 by 600 by 200 millimeters, and by build volume, that's in reference to the space that we have available for us to print. Right, this is the essentially the largest item that we could potentially print is essentially a prism that is 600 by 600 by 200 millimeters. For context, a standard consumer 3D printer's build volume is somewhere around 200 by 200 by 200 millimeters. So it gives us a lot of space, the X and Y direction, so that we can do a lot of batch prints to really experiment with all sorts of different things. The resolution of this machine, it comes out to about roughly 100 microns. By resolution, we mean just how fine we can move that printhead, right? How fine we can repeatably and reliably move that printhead and expect it to get to the intended location in X, Y, and Z. It is by virtue, it is not originally meant as a 3D printer. It's an industrial paste dispenser.
Solder paste.
Yeah, right. It's an industrial paste dispenser that's been meant for industries where the idea is that you would have your little conveyor belt on the bottom with the product that you're producing that needs to have some sort of a paste adhered to it, whether it be an adhesive or a lubricant or solder paste. But due to its rigid construction and its the high quality of its components, it makes it pretty favorable for energetics, materials, additive manufacturing. And the way that we use it in order to dispense our feedstocks, our energetic materials, is that we use a combination of a pneumatic system with a small single-screw auger system. And this auger is kind of like a very small Archimedes screw, or like a small water screw that moves material from one point to another. The machine, even though it doesn't look like your conventional 3D printer, it moves very much like a conventional 3D printer, like an FFF machine, a fused filament fabrication machine. Sorry about that. Yeah, we'll be closer to the microphone about. Thank you for letting us know, Valerie. It operates like an FFF machine, which is like your conventional 3D printer that prints with plastic. The print head moves in X, Y, and Z, dispensing material little by little until you get your final 3D printed item. So, as for how we use this machine, and especially with regards to this particular project, We used our machine, and our specific print head is known as the Techcon Auger system, right, which is a combination of the disposable single screw feed path, right, that Archimedes screw that I brought up earlier, and the motor that dispenses the material out of a disposable plastic nozzle. There's material that's loaded up in a syringe barrel that you see where right now Jorge is pointing with the mouse cursor. The material is loaded up there, and then the pneumatics or air system pushes the material through that feed path and into the chamber where the small screw is, and then that screw meters out the material precisely in precise quantities into the shape that we want it to. So we, obviously when it comes to printing with energetics, there's a lot of concern with regards to safety, with regards to proper disposal of material. So it's, as they say, practice makes perfect, right? So we used a commercial modeling compound as a surrogate. It's a popular commercial modeling compound that happens to smell like vanilla and other, interesting scents to give context. As a surrogate to establish, what are the baselines for printing with the actual energetic material and to practice a variety of different tool paths safely, right? And that gave us a lot of opportunities to also practice in general in using the machine. And we were able to discover all sorts of different caveats of working with the machine. One of the more interesting ones that we found was the sensitivity of feedstocks to gantry tramming. And by tramming, I'm referring to like the perfect square alignment of each X, Y, and Z axis, especially with regards to the printing surface. If the distance between, if the axes aren't nicely squared away, and if the print head isn't, the perfect distance away from the print surface, we get all sorts of different printing issues. And obviously, custom problems have custom solutions. No, not quite. Custom problems have custom solutions. So the picture that you see in the top left, if you could circle that, like over, yep, yep, that picture right there. Mm-hmm. We co-opted some precision laser optics equipment to make a device that would allow us to finally adjust the height of the print head. The Play-Doh pictures, the commercial modeling compound pictures that you see on the bottom, all the way there on the bottom, you can see our various attempts when we didn't have this device versus when we did. And as we determined the optimal distance, our prints went from looking not so great to being fairly workable. And if you take a look at these middle pictures over here, we had some initial promising results using the commercial modeling compound.
So having learned about the printer as much as just kind of foreseeing what type of tool pathing we get as an output from various parameters to our disposal, we had to also give a lot of attention to the safety aspects of when we were to include an energetic. So what we do with our propellant formulations is subject them to sensitivity tests, and this would include impact, friction, and ESD, whereby we know what thresholds to avoid with regard to how we're handling the material. So also going into mind with regard to safety is how we engender basically the ingredients and how we go about mixing them. So a lot of the time, right now, a lot of the time we're exploring other mixing strategies. Conventionally, you'll come across having a contact mode type mixing operation, and with that comes some safety concerns. You may have some pinch points if you're using a blade and you're trying to work up and mix your material. But right now, we're looking to develop our mixing strategies in a contactless mode. And one of those solutions for us at the moment is exploring resonant acoustic mixing, which is a mechanical translation of energy into acoustic. And that allows for ingredients to kind of mix locally by way of just vibrations that are in resonance with the material. And that allows for even entertaining higher viscosity paste that would be too difficult to mix because it might hang up on blades, for instance. So what you see here, top right corner, is the LabRAM mixer that we use. We remotely operate it, again, for safety concerns. What we went about doing with regard to our material is basically using a legacy fielded propellant that is typically processed in different means and mixed in different means to just kind of taking that wealth of information as per a recipe and translating that as a cycled, stepwise procedure with our LabRAM. So what you see here on the left-hand side is the study that we did with regard to producing a feedstock that might be amenable for our 3D printing process. So our formulation, just in general terms, includes our active ingredient ammonium perchlorate, which is an oxidizer that is found in many formulations to help with energetic output. For this particular formulation, we also had a polymer, we also had a plasticizer, and we had a mixture of different vapor pressure solvents to help with the post-extrusion of the already extruded material, such that once the material left the nozzle, it would not readily harden up by extreme loss of your solvent, but rather it would be more gradual, but also allow for interlayer adhesion once the first layer and all other layers were to be extruded onto one another. So that little study that we did was just keeping the composition of the final product the same whilst having the affordability and flexibility of changing the processing by way of adding a certain amount of solvent, and that's what you see there. We start off with a low amount of 20% all the way up to 50%, and the high extremes, 20 and 50%, were either too dry and not really supportive of good mixing, or just ended up being overly mixed and having more than what you need of solvent. whereby it wouldn't be amenable to 3D printing. 35% that we had there was basically just enough for us to be able to keep the material intact without having any material run away or precipitate out. And you can see and have a feel for the consistency coming close to the commercial modeling compound that we used in the middle, on the bottom row here.
Hello, this is David again. So once we were able to, once we had developed a technique and a plan for mixing and preparing the material, it was then that we started to begin to look into, working with the actual material with regards to printing it. Obviously, printing with the modeling compound is very fun with all of its colors, and its fantastic scent, but the real challenge came with actually working with the actual material. Like I typed out to Zachary and Howard, those are two very good questions that I can address more thoroughly at the end of the presentation with regards to the modeling compound and its relation to the energetic material. Abraham, that is a fantastic question, but I will address that at the end of the presentation. So, moving on from the modeling compound, we moved on to the actual material itself, the actual AP composite material. There's many different things that can be that need to be monitored while printing. Many parameters that need to be observed and changed for printing the material, and these are they're very important. They dictate whether or not your print is going to fail or partially print or absolutely come out perfectly. And these parameters, are not limited to the actual print head movement speed, which is the actual speed that the head moves in X, Y, and Z. If the print head is too fast, that can make a very small, thin bead that doesn't really stick to anything or cause little skips as you're printing. If you move the head too slowly, you can spurt out way too much material in a single place and you're left with a blob. The nozzle orifice diameter, that nozzle diameter dictates the available resolution that you have in both X, Y, and Z. So it especially affects your ability to print very fine features. If your nozzle's too big, you're not going to be printing very fine details. And if your nozzle's too small, then you are able to print all those very fine features, but it takes a very, very, very long time. So it's an important parameter. The extrusion rate, or how quickly we're able to move material out, as well as the pressure, depending on how the system is set up, is also very important because it affects how much it affects the rate of the material coming out and how much material is put down in a single place at a given time. Which, as I mentioned before, if put down too little or too much, you're either left with very scant beads of material or blobbing. Temperature and humidity, as well as the temperature and humidity, are two very interesting parameters that we saw because of the volatile solvent that we're using. If the ambient temperature was too high, that would cause the solvent to evaporate too quickly, and then causing the material to simply dry out and even potentially cause a nozzle clog. And if the ambient temperature was too low, the material would be way too slow to evaporate. So as we're printing, the rate of evaporation wouldn't be high enough, so we would actually be left with a very mushy print with a very little body. Keep in mind, so for most of these test prints, the majority of our results, they were performed for the most part at STP.
Right.
So, the standard room temperature, nothing too crazy. But we did have a couple of events in our lab that caused us to experience higher or even lower than normal temperatures, and we were able to observe these very interesting results. and the understanding the parameters that affect our printing capabilities with the material, and also greatly affect its quality, we're still trying to determine what they are. And what we detail here is the ones that we found that are the most prominent to us at the moment. However, that's not to say that there are other parameters that we still haven't determined that also affect print quality. Jorge right now is pointing to a couple of interesting prints that we had in our path to determining what these parameters are. These prints were our initial test prints when we didn't fully understand what it really took to print this material. This was us essentially guessing what parameters and how to set them up in order to print them. And you can see that we had very, very, very wild results, especially the one that he's circling right there. We don't know quite what happened there. The print started off as a failure. However, we let it continue so that we could document it. However, it somehow managed to temporarily write itself before failing, and then writing itself, and then failing once again. That is very much an anomaly, and we're not quite sure how it happened. Right now, Jorge is highlighting a couple of our better results that we found. While they seem okay, they have a couple of flaws that were not that are somewhat problematic. In the center one, you can see a lot of delamination between the layers, and a sort of missing material there on the side. And some of these other ones, they came out rather nicely, but they could not be repeated very easily. We tried the same settings again, and we weren't able to get a similar looking grain. Yes, and some of these also were printed with the smaller size nozzle, and lending to the very, very short grain heights. But that's something that I'll elaborate on the next slide. So, a lot of time was taken to, in our experimenting with printing, we found that these parameters that that are worth observing and that truly dictate what it actually takes to print the material, and what parameters we need to take note of so that we could create a printing envelope in which that we could essentially be able to print a bead as accurately and as neatly as possible, so that we could get the grains that we desired. So for our experiments, we decided to narrow down to 4 particular parameters. We decided to focus on the nozzle diameter, the print head translation speed, the speed at which the auger rotates, which directly influences how much mass is deposited over time, and as well as the pressure of the pneumatic system being used to introduce the material from the syringe barrel into the auger system. The figure numbers that you see here are in reference to our paper, which is also found in DSIAC Journal Volume 6, Number 3. If you haven't quite read it yet, there's a lot more information that to be found on that paper, and we explain in a little bit more detail some of those things, some of the other aspects of this experiment. Throughout this talk, I've been referring to beads, and the bead simply refers to the line of dispensed material, right? And that line of dispensed material, throughout these tests, we are looking to make sure that it is as neat, as qualitatively as neat as possible, that there's no changes in the width. It comes out nice and even. It comes out as close to the actual nozzle diameter, the nozzle orifice diameter as possible, to make sure that it adheres to the substrate as neat as possible. So the way that we decided to, in order to generate this optimal printing envelope, in order to determine what it was, as efficiently as our resources allowed us to, was to create create a small design of experiments in which we observed the 4 the 4 parameters that I mentioned before. We essentially created these small zigzag tests that would create line segments, in that each line segment would represent a different print head translation speed, and then each zigzag line represented a different auger speed. And then each set of those zigzag lines would represent a different nozzle diameter and pressure as well. So that way, we created almost a shotgun approach to determining all of these, the optimal regime for these parameters. For each of these beads, we took their mass, we took their width, we took their height, and we also did a qualitative assessment if we determined if they simply looked good or didn't look so good, or if they had any sort of weird artifacts. Jorge's currently, actually, could you zoom in, Jorge? Actually, yeah, there you go. Jorge's currently highlighting one that, to note one of those qualitative aspects that we're talking about, where it was a very nice and fine bead and close to that nozzle diameter, on paper, but realistically that qualitative assessment would tell us that it's not very good because it barely stuck to the actual substrate and came off substitute. Right, and Jorge is now currently pointing to another aspect that we mentioned, that we noted in our qualitative assessment of these beads, where we had these strange sort of printing artifacts in which it appeared like pulsing, that we made a note of. So once we printed all these beads, we measured all of our data. It was compiled and analyzed using a variety of different analysis software to allow us to determine what is the best printing envelope available to us. And there were several, and we began with that information. We began testing using. We began testing by printing the actual full grains. These full grains, we chose not to incorporate perforations at first due to us not fully knowing if we would be able to actually print it with the resolution afforded to us, and us not quite fully understanding how to print the material. But we started first by using the finer of the nozzles that we had available to us. Unfortunately, we were able to produce some grains that were close to full height and did show promise, but that was very few and far in between, simply because we had the finer nozzles had many clogging events. Mm-hmm. This caused us to go back to the drawing board in terms of how we would prepare the material to be ready to print. Starting from how it would go, how we would treat the material right after mixing and putting it into the syringe barrel, and then actually throughout the printing process to make sure that we would ensure we have close to no agglomerates that could potentially clog the nozzle. Yeah, However, despite our prudence in doing these things, we still ended up with a lot of clogging events with the finer nozzles, which caused us to need to go to the more the larger nozzle orifice diameter nozzles, which is 0.41. So once we moved up to the larger nozzles, we essentially went to almost zero clogging events, which allowed us to print several full grains without perforations. However, that then another problem arose in which we would get these bumps on the side of our grains, and these bumps are an artifact of the printing process. So each layer has a start-stop point in which the printer will start dispensing and then stop dispensing at that same point, and those bumps are caused by excess material at those start-stop points. And that comes down to motor control of our dispensing assembly. So because we have the control method for the Techcon motor system is a bit strange. It made it a little difficult to properly control it. But interestingly enough, that allowed us to discover an additional parameter to test in the future, the auger retraction time. And the auger retraction time is how long the screw will actually spin backwards in order to retract material after a dispensing command. Unfortunately, we didn't have the opportunity or the time to formally test this parameter and incorporate it into our design of experiments, but with the tests that we were able to run, we did see that increasing the retraction time reduced the severity of those bumps, and we're able to get what Jorge is currently pointing to, drastic difference between A and B bumps. Jorge is currently pointing to the rightmost grain, which is our inert baseline, where we use a traditional consumer 3D printer that prints using thermoplastics in order to print one of these grains, so that we could have a baseline to compare to. And as you can see, where Jorge is currently pointing, we got, without the perforations, we got very close to our intended goal. Good. Pan over to right. As you can see in Figure 8, we then, using what we learned from the grains printed in Figure 7, we were then able to print several more of these grains, and each one of these had very similar measurements, and we were able to essentially then be able to repeatedly be able to print these grains. We were able to achieve our FY18 goals. However, our work still isn't done with this project. We've continued our work throughout FY19. We've continued testing, printing more grains, discovering additional parameters to test, and also, more importantly, worked on incorporating printing printing with perforations in the grains so that they more closely resemble the actual intended product. And that is about it for us with regards to our slides. Thank you for taking the time to listen to us and tune in and learn about our work here at Indian Head.
Yeah, thank you guys. We appreciate your time.
Yeah, David, Jorge, as you saw, we have a bunch of questions through here, so if you don't mind, we'll kind of jump right into the Q&A.
Sure, we are more than happy to answer them.
Yeah, I think this is a pretty unexplored topic largely, so having an opportunity just to have discussion, at least hear from you, your perspective, would be pretty helpful.
Sure.
So, let's see, we'll go in order from the top. First question was, does the commercial modeling compound that you're using, does it have a similar consistency that you would see with AP and energetics feedstock?
That's really interesting. So, to keep it as concise as possible, in our experience and in talking with other people in the energetic materials additive manufacturing community, simulants have always been a tricky topic because they don't simulate the actual energetic material with regards to 3D printing very well. There's a lot of these legacy simulants that are very good for traditional manufacturing methods in which they simulate those methods very well, such as cast and whatnot. But when they're translated over to the additive manufacturing space, they don't quite work out very well. Funnily enough, one of the co-authors of this paper, Christine Knott, recommended to us using this commercial modeling compound because for her own work saw that it was a good enough simulant for practicing with. Her work isn't necessarily more directly additive related to additive manufacturing, but more so in the traditional manufacturing space. But in our testing, we found that it was good enough for us, and even more so conveniently, it was something that we wouldn't have to mix ourselves. It was cheap, convenient, water-based, and safe. And
yeah, if you want to talk about viscosities and those
the next question. Thank you, Jorge. The next question kind of related to that was: were you targeting a material a similar viscosity?
We weren't with the modeling compound. We weren't exactly targeting the viscosity per se. No, it was just being able to just process with something cheap, ready to go, just to be able to test the print parameter space that we had afforded by way of our gantry system, not so much honing in on the properties of the material, because getting there requires rheological studies that we have yet to really commence. So we really needed to pick up on something that could allow us to just start. But with regard to just purely consistency, the modeling compound did come close to the actual propellant, at least in this work. But rheological studies have yet to be performed.
The next question we had here was about the, so does the addition of the solvent affect your burn rate?
Well, we have yet to really see because, there might be some solvent that might not find its way out, but for the most part, we pick solvents that by the time we have procured a full grain, you can set it aside and allow for the remaining solvent to, be removed. But we have yet to really test this as to how much remaining solvent there is after the fact, because we have only been able to successfully print these grains just recently. So there's plenty of more work to be done before we're able to quite, in full detail to answer that. But, maybe it does. It should. But more importantly, surface area over the printed object will probably have more of an effect on burn rate at this point, just given the structures that we presented here. Each layer, will, present some additional surface area. So that may add up to being able to significantly affect the burn rate for sure. But we're getting there for sure. We're looking at that currently, but as of now, we don't have a straight answer for that.
Well, while we're talking about the solvent, the other question here was about how that affects your porosity. Seems like a significant amount of solvent.
So as for traditional methods, density is going to be different overall. Can we kind of escape a little compromise in density and still be able to procure a grain that still comes close to spec, right? That is still, again, a question to be answered. But as we improve upon our current hardware, we will try to fight for the best possible product that you can print. So this was just the first stepping stone in that direction. But yes, all of those factors will come into play for performance.
All right. Let's jump in from question to question here. So another question was about the post-processing. So it's typically, traditional AM, there's some post-processing to be done. How do you see this being accomplished for this field of EM?
That's a really good question. This is something that we have only kind of begun to explore because we're in the process, like I said, we're in the process of understanding the parameters so that we can get the most accurate print that we can possibly get. So in terms of post-processing, obviously each AM method is different, right? And each print, even individually, each print can sometimes have its own post-processing need as well. With a traditional FFF printer, such as those sold by Stratasys, or even the more consumer ones, such as Lulzbot or Prusa, those many times you can get away with. Sometimes you may need to remove support structures, you may need to remove rafts, or so on and so forth. But if they're designed properly, or if the component is designed properly, or the printer is honed in correctly, as well as all of its parameters honed in very correctly, many times the need for any of those additional printing structures are not required, and that greatly reduces the amount of post-processing for these items.
Yeah.
For the results that we're getting right now with the bumps, if we were to say this is our end result and it were to go into production right now, which it is not. This is a hypothetical. We found that you could potentially scrape off those bumps because of the material actually hardening up enough, and the bumps could be actually scraped off decently enough with a spatula. even further cleaning up the material. The pictures that we showed you actually we purposely chose not to show, the grains that we had scraped the material off of. We wanted to best represent exactly how it comes off of the printer. Go back out.
Great. Actually, if you could stick on that slide, because we do have a question from that slide.
So, sorry, but to finish answering the question, we still don't fully understand what it would entail to fully do post-processing for these materials. Will we need it? Yes, to an extent, obviously, but as we further hone in our parameters and stuff, the idea is that we could reduce the amount of post-processing required.
Good.
Yes.
Good. Thank you. So the next question here is about, on this slide, question is, where's the printing parameters and the modeling compound mix? Where do they get documented? Do you just put it on the drawing, or is there some other process for repeatability later?
I'm sorry, could you please repeat that question?
Yeah, I'm not sure I'm comprehending myself. So the question is, where is the printing, or I guess where are the printing parameters and the modeling compound mix? So where do they get documented? Do you put it on the drawing, or is there some other process for repeatability?
So, I'm assuming they mean how did we document it and how did we process that data? That we process the data obviously comes out to be a multidimensional matrix.
Let me put it this way, right? Because this is in relation to the modeling compound and how that was used to translate what was learned from that for our energetic material. I think that's kind of where it's getting at. So, as we mentioned earlier, like any one surrogate that you could devise for an energetic doesn't really quite come close, at least for 3D printing it. What we used Play-Doh really was for really just kind of gauging in the output of being able to set a speed for our print head and a pressure combination and auger speed rate that would just allow material to flow out of the nozzle. That's as far as we got with just the modeling compound, but our real energy was kind of spent on doing this design of experiments for our actual propellant. So would the modeling compounds, bead width, and mass even come close to what we were printing when we did it with our actual propellant? We didn't document that, but we definitely learned at least how to handle our propellant, having made this design of experiments just for that.
The modeling compounds serve more so for, I guess, human practice, human experience, and overall gaining an understanding of that printing, the printing process and what it takes to print the material.
All right, no, that's sufficient. The next question was about,
the question.
Yeah, I think so, from my understanding of it. Sorry, jumping in quickly, but the other questions, just because we do have a fair amount of questions, I don't know if we'll be able to get to it. We'll try to cut this off within the next 10 minutes or so, but as long as you guys are willing to stick around. But the question next up is about cleanliness. How does the cleanliness affect the print? And if it does, what do you do to control that?
I'm sorry, how does the cleanliness affect the print?
Yeah, I suppose of the material or the platform that it's being printed on.
I'm assuming they mean by just how clean the print comes out in terms of for example, the bumps and stuff and on the side, and how it affects the performance of the final item.
Oh, I was interpreting it to mean cleanliness of maybe the material that you're using, kind of purity perhaps, or maybe cleanliness of the substrate or platform that's being printed on.
I can talk to all of those aspects.
So can I.
So with regards to the substrate, obviously the clean, the cleaner you have your environment, the better it is. So the clean for this material, the best results we got was with working with a very clean substrate. With regards to the material, I can talk a little bit about it, but then I'll hand it over to Jorge to elaborate more on. We found essentially there was a lot learned in handling the material and preparing it. And cleanliness definitely came into a big factor with regards to it.
Yeah, so in terms of like, first starting to print with this material, we came at a point where we had to figure out why we kept getting clogs as our nozzle tips, and we were wondering, okay, is it just the limitations of the material properties coming into play, or was it maybe just the cleanliness even, right? So nozzle size also influenced that. So we kind of went back and kind of scrutinized our processing of the material by way of LabRAM. So one thing that we noted was because we do have a solvent in the system, the topmost layer of our material exposed to the environment would dry off, right, that material faster than the bulk. So when we were when we were transferring our material into our syringe barrel, there was the possibility then that we noted that some material that dried off made its way into the reservoir. That may have led to some of the clogs that we noticed. Another thing is that ammonium perchlorate is highly hygroscopic, so it will agglomerate fairly quickly, at least to our standards, whereby for even entertaining a solvent to choose from, some of these solvents are not 100% pure, right? So they'll also be hygroscopic to some respect, and a carrier of water, right, will definitely help with the AP or ammonium perchlorate agglomeration, and that too will influence its printability. So, those factors were looked at. We determined that they kind of got mitigated when we just used a much bigger nozzle size, and with regard to that, it was having to choose between three. So the 0.2, 0.25, and 0.41 millimeter size nozzles. The 0.2 and 0.25, no matter how much effort you put into ensuring that every step of the way leading from mixing to printing was scrutinized so that you had the best possibility of printing it, it would occasionally clog up on us. But with the 0.41, even if we were kind of loose about mixing, even then, we always managed to print a full up grain. So yeah, that was a good question.
Good. Let's see. All right, the next question is about, and I think it's probably future work, but are you planning to produce process maps for what the critical processes and parameters that you would need to create a successful print? Once you figure it out, are you guys gonna publish some process maps, or?
I wonder if that's an engineering term.
I'm not quite familiar what is meant by process map.
Yeah, nor am I.
To determine best potential build. So if you start in one area and on the x-axis of a build, you change one parameter, and on the y-axis, change another parameter. So you get a whole section of different builds according to your process parameters. In quote, determine best possible process parameters to use for a successful build.
Call it that or not?
Well, I wasn't quite sure what the question was, to be honest with you.
Sorry, and also the volume was a little low. Sorry.
Yeah, sorry about that.
Okay. Well, let me just jump. Well, there's a bunch more questions. I just wanted to try to get a couple of them here in the next few minutes. But the next question was, do you know the properties?
The properties?
I'm going to pause real quick because there's telling me there's connectivity issues. I'm getting a little nervous. There we go. Okay. Connection here. Okay, it came back for me. Properties that will result for the recipe variations.
I can only think of
properties
I can only think
will
of
result for
density.
these recipe variations.
No,
I mean
so we are sticking to the spec for the fielded item. So every ingredient is put in the way that the traditional manufacturing scheme makes it. except we're, afforded the luxury of being able to try different solvents and hope by the end of having printed the final item, most of it would have dissipated and evaporated out of the system. So you can have like the same composition as would be what's only property, I think, in variation that's of importance, density, and surely it'll be compromised because you're not pressing this material anymore, so you're not fully consolidating the material. But this is why we're researching this to see how close it comes to performance as what's out there, or how far away it underperforms.
Okay, well, let's see, we have just a few minutes, so this will be the last question. I think it's an important one. The question is, how do you perform those internal quality inspections of the final part D or piece 2? They said, will X-ray or maybe NDT be considered?
So I can speak a little bit more to that. How do we so we don't have a formalized method to do it. Like I said, we're just beginning to do these prints. It's only within the last year that we were able to generate these results, and even with our continuing result, we're steadily improving. So we don't have all the testing methods fully defined yet. With our initial tests and our initial prints, we simply took one of our samples and cut it in half using it. Also done very carefully, and we found that it was, at least to the naked eye, it seemed fairly dense. But obviously, there's the naked eye and there's raw numbers. When it comes down to raw numbers, there's a variety of methods that we have started investigating, such as using CT scanning, so that we could take a look at void regions and get I guess in a sense, a three-dimensional X-ray. I know that a lot of people in that field don't quite like to hear it referred to that way, but in a sense, get a 3D snapshot of what it actually looks like inside. And then in terms of overall density, we have been investigating just simply using an air pick to be able to get the overall density of the final printed grain. Instead of focusing on just the final feedstock or even taking a small segment of the material, find what the density is after all is said and done in terms of printing.
Good. No, it makes sense. Well, there are a pretty good amount of questions still remaining, but we're unfortunately bumping up against time here, so I want to respect the time of everybody who kind of dialed in, and maybe during a lunch hour. So for everybody whose questions were not yet answered, I would encourage you to either deliver them over DSIAC.org. It's a technical inquiry, and we can answer them, or get David and Jorge to answer them. I'm sure David and Jorge, you guys wouldn't mind.
No, not at all. We're actually excited to answer those questions.
Correctly, yeah. All right, you get that.
We're extremely flattered that this many people tuned in despite the issues with DCS.
So please, you can get them to David and Jorge. They could answer them directly. We can route that to them through DSIAC. But we've been recording this. Hopefully the recording works, and we're able to put that out. In either case, we'll follow up with an email or notification to everybody just to thank them and make sure they know where more information is available. So thank you all for dialing in. Jorge, David, appreciate you guys taking time to put this together and deliver this presentation and talk with us.
Once again, thank you, Brian, for hosting us
and
being able to present our work. And thank you, everybody, for tuning in. We really appreciate you taking the time to hear us out about our work that we're very excited to talk about here.
All righty. Well, thank you, everybody. We're closing it out for today. Appreciate it.
Thanks, guys.
Thank you.